Welcome, AP Chemistry students, to Unit 8. Today, we will be talking about the basics of acid-base chemistry. In this course, we have talked about putting substances in solution. We ended the last unit talking about how an insoluble salt will set up an equilibrium and dissociate into its ions. Those aqueous solutions all take place in water, but when you add something to water, you will favor a natural reaction that occurs in water, the dissociation of it. Water will run into other water molecules on a very small scale and produce two ions of its own. A hydrogen can transfer from one water molecule to the other, making hydronium or hydroxide. And I said again, this is a very small amount of water molecules that do this. At room temperature, pure water has a self-ionization constant of 1 × 10 to the negative 14th. About 1 in every 10 billion water molecules will collide with one another to form these two ions. So again, very small. However, anytime you add something to solution, you're going to favor the production of those ions, and that's where we come up with acids or bases. If you add something to solution that gives off hydrogen ions, you'll make more hydronium, and we call those substances acids. Acids release hydrogen ions. So generally speaking, the formula for an acid is a hydrogen ion in any anion, because when placed into solution, the hydrogen ion will dissociate from the anion. On the other hand, a base will be anything that makes more hydroxide ions. And generally speaking, the formula for a base is some metal ion paired with a hydroxide ion. So when you place them into solution, they release those metal ions and the hydroxide anion. Now, this definition was given to us, or this explanation was given to us by a man by the name of Arrhenius, the same person who calculated activation energy. In the next unit, when we talk about thermodynamics and you calculate activation energy, we'll talk about Arrhenius' equations. But Arrhenius was really interested in acids and bases and how they dissociate. However, Arrhenius' definition applies mostly to things that follow the examples that an acid is anything that starts with a hydrogen and has some anion, and a base is anything that has hydroxide in it. And it can't really explain something like ammonia. Ammonia is a base. It causes a solution to become very caustic. So why is ammonia a base? It doesn't have hydroxide in it, so that kind of stumps Arrhenius' definition of an acid or a base. However, two scientists published around the same time the idea that perhaps it's not the fact that something has hydrogen and can donate it, perhaps it's the fact that something in solution can pull those hydrogens or donate them. And those two scientists were Bronston and Lowry. Johannes Bronston and Thomas Lowry both published a paper around the same time, coming up with the idea that since acid-base chemistry has to happen in water, the movement of those hydrogen ions is ultimately what determines if something's an acid or a base. So, for Bronston and Lowry, an acid is anything that donates a hydrogen. So a hydrogen donator is known as an acid. If something accepts that hydrogen, it's a base. Now keep in mind that a hydrogen atom is simply, with no electrons, a naked proton. So we often just say an acid is a proton donor and a base is a proton acceptor. And these set up equilibriums. So the reason that ammonia functions as a base is because it's able to remove a hydrogen from water, becoming a proton acceptor or a base. Now, when it does that, it becomes ammonium, the ion. Since this is an equilibrium, ammonium can act as an acid if the reaction were to run backwards, donating a hydrogen to the hydroxide that the forward reaction produced. So you end up with conjugate acid-base pairs in a Bronston-Lowry acid. So in the forward reaction, water is acting as an acid because it is donating a hydrogen to ammonia, which is acting as a base. In the reverse reaction, ammonium is donating a hydrogen, therefore it is an acid, to hydroxide, which is the conjugate base of water. So if you're ever asked what is the conjugate acid of something, simply add a hydrogen to it, because if it's a conjugate acid, that means it was a base in the forward reaction, so it must have picked up an hydrogen. If you're ever asked what is the conjugate base of something, that means it was an acid in the forward reaction, so remove a hydrogen from it. So in your packet, we have some of these already worked out for you. For this, it's not necessarily an example, but let's show how each of them function as an acid or base. Even though they are labeled here, let's show. Nitric acid is an acid. It donates a hydrogen to water, making it an acid. In the reverse reaction, though, nitric acid becomes the nitrate ion, and therefore will accept a hydrogen from the hydronium produced. So you end up with an acid and conjugate base pair. Water acts as a base. It is a proton acceptor in the forward reaction. In the reverse reaction, it becomes hydronium, which is the conjugate acid. We just talked about the reaction between ammonia and water. This reaction simply shows it in reverse. So ammonium can donate a hydrogen to water. Therefore, ammonium is acting as an acid in the forward reaction, but in the reverse reaction, ammonia has to accept a hydrogen. Therefore, it's acting as a base. So we end up with a conjugate acid-base pair. Water accepts that hydrogen and is therefore acting as a base in the forward reaction. As hydronium, it's acting as its conjugate acid. In our final example, we have phosphoric acid that's already lost a hydrogen. Phosphoric acid can lose another hydrogen to water, again, by acting as an acid. In the reverse reaction, biphosphate has to accept that hydrogen. Therefore, it's acting as its conjugate base. Water, once again, is accepting a hydrogen, therefore it's a base, as hydronium is its conjugate acid form. So, for example 1 in your packet, we have a couple questions. The first one says, here is hydrobromic acid and ammonia producing ammonium and the bromide ion. Label what is the acid, what is the base, the conjugate acid, the conjugate base, and show the movement of hydrogens, much like we've done. So, hydrobromic acid becomes bromide, and ammonium comes from ammonia. So there's our pairs. How does hydrobromic acid become bromide? It must lose a hydrogen to ammonia. Ammonia, therefore, is acting as a base, while hydrobromic acid is being an acid. In the reverse reaction, ammonium loses a hydrogen to the bromide ion. Therefore, ammonium is acting as an acid in the reverse reaction. So this is a conjugate acid of the ammonia base. The bromide ion is accepting that hydrogen, so it's acting as a base, and it is the conjugate base of the hydrobromic acid. A quick side note here, all the examples have had the hydrogens going from the left to the right. That is a coincidence. It is not factually true. You have to look at each question, each formula, in order to figure out which way the hydrogens move. What if we're not given an equation? Can you determine what something's conjugate acid or base is? So just think of it as it's the opposite. If something is a conjugate base, that means it was an acid in the forward reaction. So as an acid, what would something have to do? It would have to give up a hydrogen. So for the conjugate base of hydrosulfuric acid, we'll just lose one hydrogen. So the conjugate base of hydrosulfuric acid would be bisulfide. If we want the conjugate acid, that means it was a base in the forward reaction. To be a base, you have to accept a hydrogen. So if nitrate were to accept a hydrogen, it would become nitric acid. Unfortunately, Bronston-Lowry's definition of an acid or a base does not cover every single acid-base reaction in the world. For example, boron trifluoride is an acid. However, boron trifluoride cannot readily donate a hydrogen. There's none there. So how is boron trifluoride an acid? It has to do with the Lewis structure of boron trifluoride. Boron trifluoride has room in its orbital for extra electrons. Those extra electrons could come from a pair of hydrogens or from a lone pair. Boron trifluoride is able to neutralize ammonia. It was Albert Lewis, the same one that gave us Lewis diagrams, that said, we could think of it as opposite. If something's a proton donor, because there's a conservation of charge, it also has to therefore be an electron acceptor. So an acid you could think of as being simply anything that will accept electrons. If something is a proton acceptor, because there's a conservation of charge, that would mean that it donates electrons, but it becomes more positive. So a base would be something that could donate electrons. This can get very complicated very quickly. The good news is that on the AP exam, you really only need to know this by definition. You are not going to be asked to demonstrate whether something is a Lewis acid or base. You will get a multiple choice question that says, which of these three is a classic Lewis acid? A classic Lewis acid is boron with 3 of anything. A classic Lewis base is ammonia, but nitrogen with any 3 halides would also satisfy that concept. So again, you do not need to know this beyond the definitional term. You don't have to be able to explain that this lone pair can come in here and form a coordinate covalent bond. That's a story for second year chem in college. So, with that being said, you are able to do page 15 in your packet. You are going to show the movement of hydrogens in the forward and in the reverse reaction, demonstrating whether something is an acid or a base in each one. Remember that in our examples, we have shown the hydrogens moving from the left to the right. That is a coincidence. It will not always work that way. You need to look at the before and the after that hydrofluoric acid becomes fluoride in order to figure out which one's an acid or a base. So with that being said, please pause the video and complete page 15. Now, when we've been looking at acids and bases, we can define an acid or base depending upon how many hydrogens or hydroxides it can accept. When it comes to an acid, if something is monoprotic, that means it has a single hydrogen that it can donate. In an Arrhenius acid, monoprotic acids start with hydrogen, and it's that hydrogen at the beginning of their formula that can be donated. In something like acetic acid, the hydrogen in front of that formula is what can be donated. So when you look at the structural formula for acetic acid, that hydrogen at the end is the one that's being donated. That's because the acetate anion is going to stay together. It's not going to dissociate. Something that is diprotic would have, you guessed it, 2 hydrogens it can donate. So for example, oxalic acid or dichromic acid. There are 2 hydrogens that they can donate. They will only donate 1 at a time. So if we have dichromic acid, we would only show it losing a single hydrogen at a time, because only 1 is going to leave at a time, and then we need to look at different equilibrium expressions to determine if another would be donated and when that would happen. Beyond that, we are not going to go much further. We're not going to talk about triprotic or quadriprotic. We're just going to say anything after 2 we will define as polyprotic. All right, so for example, phosphoric acid is the only one that you might come across. All right, same with bases. We will focus on either mono or diprotic bases, things with up to 2 hydroxides that we could donate, but we're not going to go much further than that. Now, if something can accept a hydrogen or donate it, it's known as being amphoteric. So for our examples, and on page 15, you saw where water could accept a hydrogen to produce hydronium, or you saw how water could donate a hydrogen to produce hydroxide. So water is an example of a substance that is amphoteric. It can donate or accept hydrogen. It's just one of many substances. A lot of conjugate bases are amphoteric. For example, bisulfate. Bisulfate could pick up a hydrogen, making the conjugate acid sulfuric acid, or it could donate a hydrogen, making the conjugate base the sulfate ion, because it has space to drop or pick up another proton. In a dissociation equation of an acid, we simply show how something either picked up or gained that electron 1 at a time. So, if we wanted to show the dissociation equation of hydrochloric acid, we could donate 1 hydrogen from it. So the dissociation equation for hydrochloric acid would be hydrochloric acid in solution will break up and be formed from hydrogen ions and chloride ions in solution. There's our dissociation equation. We don't talk about the water unless we are talking about a hydrolysis, but that is later in this unit, so don't panic about it just yet. We're just going to show the donation of a single hydrogen or hydroxide at a time. So, for the next one, acetic acid. Again, it's the hydrogen in front that we will donate because the acetate ion is not going to separate. So for acetic acid in solution, it will break down and come from a hydrogen ion and the acetate ion. For ammonium, the ammonium ion will dissociate into a hydrogen ion and ammonia. For the aniline ion, we can drop a hydrogen. We'll drop one from here, just like how in ammonia we dropped from the end here. In amine group is at the end of this. That amine group is what picked up this extra hydrogen. So C6H5 and H2 can give up a hydrogen. And lastly, we have the complex hydrated aluminum 3 ion. If we were to lose a hydrogen, it's going to come from one of these waters. So we would end up with a hydrated aluminum 3 that lost a hydrogen. This one's a little complicated. Notice that there's a conservation of charge on both sides. You won't get something that complicated, most likely, on your AP exam, but just in case you ever see it, there's an example of a complex ion and its dissociation. With that, you'll be able to do all of page 16 ignoring the KAs or KBs. So please do page 16. Do not do the second half. We will finish page 16 next class. I will see you when we talk about the strengths of acids or bases.